Let's try. All right, if you guys have any question, go ahead and write it. All right, if you have any questions, just put it in the chat box. Do you guys hear me? Can you say yes in the participants? Hit yes if you can hear me, please. Thank you. Awesome, thank you. Let's check the time. Now we're gonna start in a few minutes. Ask your questions if there are any. We are also live on YouTube. I'll share the link at the end of the meeting with you once YouTube processes the video. Right now, 13 people. So how is the quiz coming? You can put it in the chat box, unmute yourself simply. You still have the quiz, right? Quiz number 5. It's available till the end of the day. Don't forget that. So last week's quiz was sort of like off the schedule, but we're gonna go back to the original one. Well, don't say anything about the questions, by the way. Don't give any details because the quiz is still going on. And tomorrow you can work the quiz with back during the rest station, just so you know. Let me open up another camera view. All right, good. Awesome. I'm going to also start recording in Zoom's cloud, so hopefully I can share that with you too. But YouTube Live is the best bet currently because Zoom erases all the cloud storage. after a certain number of recordings. I download them though, and I try to edit them, but everything depends on the available time. So, all right. So why don't we go ahead and start? So last lecture we had section 4.1 covered all the way. So today we're gonna see another application of differentiation. It's called Rolle's theorem, and as well, Rolle's theorem has a simple extension, and it's called the mean value theorem. So we're gonna have, in fact, two different things covered today. One is the Rolle's theorem, and the other one is the mean value theorem. And like the other theorems that we had earlier, like intermediate value theorem, for example, we're going to check all the conditions of the theorem before we decide if we can apply the theorem for the given question. So let me just go ahead and then talk about the Rolle's theorem a little bit. So essentially, if you have a continuous function on a closed interval AB, we must have both a minimum and maximum, because this is what we proved or what we stated in the last lecture, right? Continuous function on a closed interval must have both maximum and minimum. And those values can occur at the endpoints as well. So now let's state the Rolle's theorem. So let's say like we have a continuous function on the closed interval AB. And we need an extra condition here called differentiability, okay, on the open interval AB. So two conditions. One is continuity. I'll just write it here. One is the continuity on the closed interval. Second, we want the function to be differentiable on the open interval AB. And third, we want the endpoints providing you the same function value. In other words, f of a equals f of b. So if all three conditions are met, then by Rolle's theorem, it's guaranteed that there's at least one number c. So you just imagine interval AB like this. And there's going to be somewhere here a c, number c. It could be more than one, by the way, but this theorem guarantees at least one, such that f prime at that point is going to be exactly equal to 0. In other words, you're going to have a horizontal tangent line, okay? Horizontal tangent line at x equals c is guaranteed by the theorem. Again, one more time, I'm telling you, we want f to be continuous, okay? We want f to be continuous, that's number one. Number two, we want f to be differentiable. That means you can take the derivative of the function without a problem on the open interval AB, okay? Check mark. And lastly, we want f of a is exactly equal to f of b. So if the function f attains the same value at the endpoints, then it's guaranteed that there's going to be a horizontal tangent line at an interior point C. And this could be more than one. So let's just have like a graphical explanation of that. So assume that you start with a continuous function on the closed interval and differentiable on the open interval. And if the endpoints provide the same function value, then there must be at least one x value or c value in between a and b, such that you have a horizontal tangent line. Like in this example, as you see, I have a very nice continuous function because you graph the function without taking your hands off, right? And then it's also differentiable because you can find a tangent line at every point without a problem. There's no jump, there's nothing going on in this graph, right? And as you see that f of a and f of b are the same, right? The function attains the same value at a and b, then as you see that you have a horizontal tangent line. In fact, this is the relative maximum value of the function on this interval. Okay, this is one simple graphical outlook of that. Can you, like the question here is that, can you give up on the theorem. For example, can you give up on the continuity? Can you give up on the differentiability? Can you give up on having like f of a equals f of b? Well, in certain cases, you can sort of like give up on those properties. You may still have a horizontal tangent line. You may still have a relative maximum, but this theorem says that once all three conditions are satisfied, it's for sure that you're going to have a horizontal tangent line. And here is sort of like one example where the differentiability requirement is dropped from the Rolle. And as you can see from the graph, that f still have a critical number in AB, right? This is like C, where f prime does not exist. We discussed about it because if you have a cusp type behavior or sharp turns, as you see, f prime is not defined, so that makes C a critical point, right? That makes C a critical point. You still have a relative maximum, if you can see from the graph, but as you see, you don't have a horizontal tangent line. It's not like you have the endpoints providing you the same value. F is still continuous, but not differentiable. So in this case, as you see, like there is no horizontal tangent line, even though you have a relative maximum value achieved within the interval AB. Okay. So if you give up certain conditions of the theorem, so at the end, you won't be able to see a horizontal tangent line type behavior. Okay. So that's why we have to check all three conditions and then make sure like all are satisfied. Then we're safe to say like we have at least one horizontal tangent line in between the endpoints. Okay. So here is one example of an application of the Rolle's theorem. So let's try to go through this. It's asking you find two x-intercepts of the quadratic. So let's find two intercepts of the function and show that f prime of x is equal to at some point between the two x-intercepts. And the reason why we're looking for x-intercepts in this case is because we know that at the intercepts, let's say like we have let A and B be the x-intercepts. We're going to find them, but I'm just saying intercepts. And what is the commonality between the x-intercepts? Well, we have f of a equals f of b equals 0, because at the x-intercepts, the function attained the value of 0, right? So going back to the third condition here, it's automatically satisfying, right, at the x-intercepts, because a here is one x-intercept, b here is another intercept, and we know that f attains the value of 0. So all we need to check to apply the Rolle's theorem at the end is continuity and differentiability of the function. Okay, but before we hit the road, why don't we just find those x-intercepts by setting quadratic to 0? Okay, so one way to find the x-intercepts or zeros of the quadratic is to use the quadratic formula, or I'm going to use the shortcut, but go ahead and use the quadratic formula if you want to. It's the formula is minus b plus minus b squared minus 4ac over 2a, right? And then a equals 1, b equals -3, and c equals 2. And then don't get confused here that I used the AB notation, and these ABs are totally different ABs, okay? So this is just the quadratic formula for a equals 1, b equals -3, and c equals 2. And in this case, you can apply the quadratic formula, but I'm going to just factor this out as x minus 2, x minus 1, so that you're looking for like two numbers whose product is 2, and the sum is -3, and those numbers are -2 and -1. So this is the right factorization, and it does imply that x equals 1 and x equals 2 would be the roots, zeros of the quadratic, and go ahead and then have the interval 1, 2 to start with. So I'm going to choose a to be 1, b to be 1/2. So a to be 1, I'm sorry, and b to be 2. And here's the closed interval that the Rolle's theorem mentions. Okay, closed interval AB, right? It's mentioned here. So these are the zeros of the quadratic where the quadratic hits the x-axis at those points, right? And now I can go ahead and conclude that f of 1 and f of 2 are all zeros, as I just said here, right? All right. And then two other things to check. F got to be continuous on the closed interval. Well, this is a quadratic, right? Quadratics are continuous and in fact differentiable everywhere, not necessarily just on the interval 1 and 2, but everywhere on the real axis, right? So in fact, all three conditions of the theorem, as you see, are satisfied, right? Quadratics are continuous everywhere, and in particular on the interval 1, 2, differentiable as well. And f of 1 equals f of 2. So that means there is going to be a number c such that f prime of c equals 0. So there's going to be a slope 0 for the tangent line. Okay. So that's exactly what I just said. Since f1 equals f2, which is equal to 0, from Rolle's theorem, it's guaranteed that there exists at least one, there could be more, but at least one c such that f prime of c equals 0. So now let's find that c point, okay? We know it exists, let's just try to find that. First off, f of x equals x squared minus 3x plus 2, okay? And I'm gonna look at f prime, which is 2x minus 3. And I'm gonna set it to 0, okay? And solve for x, and that's going to be 3/2. And 3/2 is in between 1 and 2, which was guaranteed to exist by the Rolle's theorem. So once you know it exists, you can go ahead and find that c number. So this is your c in the Rolle's theorem, right? But without knowing it exists, you don't want to, do all the calculation for f prime, because here the function is quadratic, which is easy to deal with. But if it's too complicated, you don't want to spin your wheels for finding nothing, right? But we know from the Rolle's theorem that c exists, at least one of them. So you go ahead and then find c to be exactly equal to 3/2, and then there's no other points for which you have the horizontal tangent line. And to see, or to sort of like have a reality check, why don't you graph this function and visually convince yourself that at 3/2, you have a horizontal tangent line, as you see. Okay, so at 3/2, you have a horizontal tangent line, as you see. F attains the same values at the endpoints 1 and 2. And in between 1 and 2, you have the slope achieved to be 0, or you have a horizontal tangent line, and that point is in fact 3/2. Okay. So this is one application of the Rolle's theorem. Do you guys have any question? Yes, if you have any, otherwise hit no, so that I can get feedback from you. All right, so far you're good. Awesome. Thank you. Thanks for the feedback. All right, so let's see if I want to go through another example. So I'm going to go through one example, but you can sort of complete the other one by yourself. All right, let's just have this example gone through. Let's say like we have two different functions. One is defined by the absolute value, and another one is defined as like a trig function, sine 3x, and then you have different intervals, obviously. So in the question statement, it says like determine if Rolle's theorem can be applied to the given function on the closed interval. If it's applied, then find all values of c in the open interval AB such that f prime of c equals 0. Okay. If Rolle's theorem cannot be applied, explain why not. Okay. So I'll give you like 30 seconds to think about this problem, especially for the first case. Let me just open this up for you. So you have the absolute value function defined, 3 minus the absolute value x minus 3. And the closed interval is 0 and 6. Okay. And here's the statement of the Rolle's theorem. And you tell me if this function is a nice one, so that or not, in terms of satisfying the conditions of the Rolle's theorem. And what are the conditions again? Well, f got to be continuous and differentiable on the open interval, and then 3 f of a has equal to f of b. Okay, so you go ahead and visually check if 3 of those conditions are satisfied. I'll give you like 30 seconds to think about it. And if you want to, you can graph the function, if that's going to help to see the continuity or differentiability. And absolute value functions are in terms of their graphs. They could be continuous, but you may have sharp turns. Whenever you see an absolute value function, you should sort of like remember that you may have sharp turns. All right, so what do you think about the continuity? Who wants to speak up? Is the function continuous? Let me see your answer first. Like yes, yeah, like if yes, hit the green button, yes, and then if no, hit the red one. What do you think before we start going through that? So I have like 5 yeses and 6 yeses. And is there any no's? Okay. Well, one thing is that obviously the interval is 0 and closed interval. A equals 0, B equals 6. Let me use another color. Not a good one. Okay. And for this function, we in fact went through this in chapter 2. Continuity requires like 3 separate conditions, right? F must be defined on the interval 0, 6, which is the case in fact, right? F is defined for all x in this interval. And 2, limit should exist, right? Yeah, you can go ahead and calculate the limit of the function at any point coming from the interval, right? Limit value, in fact, let's say like if x goes to c, 3 minus the absolute value of x minus 3 equals the function value at the same point. So in other words, 3 minus c minus 3, and whatever c is, okay? So what I'm trying to say here is that the continuity conclusion is easy because all 3 conditions are satisfied without a problem. Another way to see that, or another way to show me that f is continuous, you can graph the function, right, on the specified interval. Let's say like you have 0, 0, and 6, 0, and on this interval you see like you have one linear graph up until you hit x equals 3, right, and then you have another linear graph on the other side of 3. So it's a continuous function because you just keep sketching the graph of the function without a problem, without taking your hand off. The problem is the problem is not the continuity but differentiability, because at x equals 3 there's a sharp turn, and whenever you have a sharp turn, remember the different. So for 1, you have a check mark. For 2, f is not differentiable because you have a sharp turn, right? F is not differentiable at x equals 3, which is an interior point. And one of the conditions of the theorem says like f must be differentiable everywhere on the open interval. 0, 6, but at 3, well, it's not differentiable, so one condition fails. I don't even need to check the last condition because the second condition fails to hold true. So here the conclusion is that I can't apply the Rolle's theorem, at least for this function. So the conclusion may not hold true. So I can't apply the Rolle's theorem again. In other words, I don't know if there's a C for which f prime of C equals 0 based on the conclusion of this theorem. So since I can't apply the theorem, I don't know if there's a horizontal line. Okay, so this is sort of like the conclusion for part A, that Rolle's theorem, in other words, is not applicable for this function. Okay, so cross mark, I can't apply the Rolle's theorem. How about the second example? You have sine 3x and the interval is pi over 2 and 7 pi over 2. So why don't you start thinking about if you can apply the Rolle's theorem. So that means if you were in the exam, you would show me number 1, number 2, number 3, all 3 conditions satisfied. You should put like a check mark all the way. Check mark, check mark, check mark. And then now I'll give you like another 30 seconds to think about it. So you're going to check continuity on the closed interval. This is your A, this is your B, right? So sine 3x should be continuous on the closed interval pi over 2, 7 pi over 6. And second, f must be differentiable. That means you should be able to take the derivative of the function everywhere in the open interval pi over 2, 7 pi over 6. And lastly, you will check if f of pi over 2 equals f of 7 pi over 6. And for number 3, you can in fact use your calculator, right? F of pi over 2 equals f of 7 pi over 2, 7 pi over 6. Use your calculator to verify this condition, or use the unit circle. Okay. To answer the differentiability question, again, you should be able to take the derivative of the function. But you have to show me that f is differentiable, means f must have the derivative everywhere on this interval, pi over 2 and 7 pi over 6. All right, here we go. You tell me if f is continuous. All right, what do you think? F is continuous. And how do you say it, or how do you write it? Either in, I mean, just say like f is continuous. Is that all? There are two ways to show if you were in the exam. One is to check the continuity conditions. So f must be defined, f must have a limit at every point, and f of or the limit value is exactly the same as the function value. This is one way, which is the rigorous way to prove it. Another way is to graph the function and saying like there's no jump, there's no break in the graph, right? So it's a very smooth, continuous function. For the x min to be pi over 2, x max to be 7 pi over 6. So when you graph this, make sure x min is going to be the left endpoint, x max would be the right endpoint for the function. Okay, so f is continuous because, as I said, by looking at the graph, you see that there is no break. But in the meantime, limit of the function at any c coming from this interval is found by function evaluation, right? Sine 3c. You can also say this, right? For any c in pi over, in fact, closed interval pi over 2, 7 pi over 6. Okay, so that's why we have the check mark for the first condition. How about differentiability? What do you think about differentiability? Is f differentiable? If so, how do you say it? Like, how do you say that? Or how do you convince me that f is differentiable? Because saying f is differentiable doesn't mean much, because then I ask you, like, how do you know? Then you have to tell me exactly the right, if you were in the exam, for example, or in the quiz. Is there anyone who wants to speak up? Oh, there's no sharp turn. Yeah, that's one thing you can say, but it's not enough. Because differentiable means that f has the derivative everywhere on the open interval pi over 2 and 7 pi over 6. If you say that, okay, I'm going to ask you, like, then what is the derivative of the function, right? If you can take the derivative of this function without a problem, then f must be differentiable, right? Well, this is a sine function, and you can apply the chain rule, right? The derivative of sine 3x is cosine 3x times the derivative of the inside, right? That's 3, so it's 3 times cosine 3x. And the sharp turn either, as Steve mentioned, and there's no, well, saying there's no restrictions is not enough, but you should convince me in a way that, okay, well, there's no sharp turn, obviously, but the best way to say it is just, going back here and saying, like, f prime it can be found without a problem by taking the derivative of the function, which is 3 times cosine 3x. And since you can find a derivative all over, and there's no point that makes this function undefined, right? Because cosine 3x as well is a very nice function. So second condition is already satisfied. Okay. All right. How about the last condition? You should use your calculator, right? Go ahead and then find f of pi over 2. F of pi over 2 is sine 3 pi over 2, and f of 7 pi over 6 is sine 3 times 7 pi over 6, right? So that is sine 7 pi over 2. Okay. So the question mark here and another question mark, are these guys all equal to 0? Can you use your calculator and simply verify that sine 3 pi over 2 and sine 7 pi over 2 spit out the value 0? Just use your calculator, convince yourself, and there you go. So all 3 conditions are satisfied. Check mark, check mark. Okay. So if you used your calculator, don't forget to put it in the radian mode, by the way. Then you can visually verify that all 3 conditions of the Rolle's theorem are satisfied. Number 1, number 2, number 3. So it's guaranteed by the theorem because it's sine 3x, right, Dalton? So it's sine 7 pi over 6 times 3, which makes it 7 pi over 2. Okay. So in other words, let me just write it here. So this part here. So f of 7 pi over 6 sine 3 times 7 pi over 6. Let me just use star here. So that's sine 7 pi over 2. Okay. All right. So that it's guaranteed that f prime is going to be 0 at some interior point. So there's going to be a c in between pi over 2 and 7 pi over 6, for which f prime of c equals 0. Okay, let's find that c. Or c's. Let's see how many we have. All right, so f prime, we just found that. It's 3 times cosine 3x. Now we want to set this to 0 and solve it. Okay. And the solutions coming out of this equation would be good candidates for these C guys here. And we want to make sure, like, whatever the solution or solutions we get out of solving this equation should be in the interval pi over 2 and 7 pi over 6. Okay. All right, so divide both sides by 3 so that you have cosine 3x equals 0. And here we go. We go back to pre-calculus, solving a trig equation. And you got to remember when cosine is 0. At this point, you can use your calculator and then find 3x to be exactly equal to cosine inverse of 0 or arc cosine of 0, because this is how you treat a trig equation if you want to use arc sine or arc cosine. In this case is arc cosine. So arc cosine 0 should be equal to 3x. Okay. Can you go ahead and then punch in arc cosine 0 in your calculator and tell me what it is? So what is cosine inverse 0 or arc cosine 0? And just use the chat box to type it in. In other words, whose cosine is 0? And whatever comes out of your calculator would not be enough, in fact, to solve this problem, because the safest way to handle this problem is to use the unit circle, by the way. Okay, to use the unit circle. So pi over 2 is what comes out of your calculator, right? So thanks, Vanessa. Pi over 2 is what comes out of your calculator, but also you know that cosine is 0 at 3 pi over 2. Okay. You can go ahead and then look at cosine 3 pi over 2. That's 0. So in other words, if you look at the unit circle, cosine function is always the x coordinate of the points on the unit circle. So at this point and at this point on the unit circle, you will have cosine achieving the value of 0. So in other words, I have two instances where cosine is 0. One is pi over 2, which comes out of your calculator, and another one is 3 pi over 2, which doesn't come out of your calculator. Okay. So here we go. Let me just erase this portion so I can continue writing on the same slide. Use the same color here. So 3x could be pi over 2, but also could be 3 pi over 2. Okay. In fact, you can add more points if you want to. So, well, like pi over 2, this is pi over 2. This is 3 pi over 2. If you have another round on the unit circle, this could be 5 pi over 2. This could be 7 pi over 2. Or you can go with the minus direction, in the other direction. Okay. So this could be like maybe minus pi over 2. Okay. So it's better to sort of for you to remember the unit circle business. Okay. Let's go with these two values and see if there's anything popping out of that. So this is 3x, by the way. So 1x is going to be pi over 6, and the other one is going to be 3 pi over 6. In other words, pi over 2. Okay. So as you see, pi over 6 is not in this interval, right? Pi over 6 is not in this interval. So I can immediately discard that. What about pi over 2? Well, pi over 2 is not in this interval either, because C cannot be an endpoint, right? So these guys don't split anything at all. So that's why we need to go to the second set of values here on the unit circle. And you have 5 pi over 2 and 7 pi over 2. And again, these are all 3 x's. So one x is going to be 5 pi over 6, and the other one is going to be 7 pi over 6. Okay. Well, 7 pi over 6 cannot be a good candidate either, because that's the endpoint. right? Endpoint is not applicable, is not coming out of the Rolle's theorem statement, right? Because C must be an interior point. And the only candidate I can take is 5 pi over 6 here. Okay. And you can visually verify that by the graph of the function. As you see that the endpoints right here, so you can put your x min and x max to be like pi over 2 and 7 pi over 6. Okay. And do it. This is pi over 2. In fact, there's a typo here. Pi over 2, 7 pi over 6. And as you see that 5 pi over 6, you achieve a horizontal tangent line where the slope is 0. Okay. This is a very nice question for you. So like retrieve your trig knowledge, especially in terms of using the unit circle, because as I said, if you don't use the unit circle and if you try to use the calculator value, that may mislead you, and it doesn't probably take you to the right result at the end of the problem, right? So to sort of like bypass that, you can use the calculator value once to pinpoint at least this point, but then the other points should come out of your trig knowledge, right? Because you also have 3 pi over 2, and then you have another rotation clockwise or counterclockwise to sort of like pinpoint other points that would potentially yield a candidate that makes cosine 0. Okay. And I totally recommend you to sort of like watch the video of this lecture again and go back and then simply convince yourself that you understand all these steps here. Okay. Any question at this moment? Any questions so far? And this video is already on YouTube live, so you can go ahead and then rewatch the video once it processes. And if you haven't signed up for my YouTube channel, it's the best time to do it. It's AOOZER, and sign up when the YouTube processes the live video. You will be able to get a notification, and you can watch it in your own convenient time. And I'll try to share the link to you at Blackboard. Okay. All right, so no questions, so we can like continue. And one another application of derivatives in close ties with Rolle's theorem is called the mean value theorem. Let me just bring up the definition of the mean value theorem, or the statement of the mean value theorem. So let's just read through that. F is continuous on the closed interval AB, so that's one condition. And F is differentiable on the open interval AB. Here we go, second condition. Okay. If T conditions are satisfied, and this theorem says that there exists a number C interior point in the interval AB, we call that interior point C, such that F prime of C, which is the slope of the tangent line at the point C, is exactly equal to F of B minus F of A divided by B minus A. Okay. So if you have F and if you have the closed interval AB, what is the meaning of this ratio? Do you guys remember from chapter 2? So what is the meaning of F of B minus F of A divided by B minus A? Who's going to tell me? What does that represent geometrically? Anyone? Limit definition. Well, there's no limit here to start with, right? There's no limit. It's just a ratio of two numbers. One is F of B minus F of A, and the other one is B minus A. So what did we call this ratio earlier? Again, no limit going on at this moment, so just think it that way. So what is f of b minus f of a? It's rise from a to b, and then this is the run, right? Rise over run, correct? Rise over run. And in fact, this is the slope of the secant line from A to B, right? Everybody agrees? Slope of the secant line from A to B. All right, so this theorem says that if two conditions are satisfied, we're not asking f of A and f of B to be 0 in this regard. But the slope of the secant line is achieved at an interior point. So what that means is if f satisfies these two conditions, you can check this graph as an example, by the way. Oops. Here we go. The slope of the secant line that connects two endpoints 1 and 4 in this graph, right? This is the secant line. And the slope of that is f of 4 minus f of 1 divided by 4 minus 1. Right? The same slope is attained by an interior point, so that you will have a tangent line that's exactly parallel to the secant line, connecting the ends on the curve, endpoints on the curve. Okay. So this is another application of Rolle's theorem, in fact, because going back to the description of the mean value theorem, if I do add the third condition, which is f of a equals f of b, then this theorem becomes the Rolle's theorem, right? If I add this condition, this is the Rolle's theorem. And if that is the case, if f of a equals f of b, slope of the secant line is going to be what? 0. So f prime of c is going to be 0, which is exactly what Rolle's theorem says, right? So if you have f of a, f of b exactly the same, so that the secant line would have the secant line here, as you see, have the slope 0, and then the same slope is achieved by an interior point, as you see, right? Here at the end point, you have f of a equals f of b, right? So the f prime to be 0 is achieved at some interior point, okay? So mean value theorem and the Rolle's theorem are essentially the same things, and I think mean value theorem is more general to me, because slope of the secant line, it could be 0 or non-zero, is achieved at an interior point at least once. Okay. And this example is a good example. In fact, let's just go through that real quick. You have the f to be 5 minus 4 over x, and the question is asking to find all values of c in the open interval 1, 4 such that f prime of c equals the slope of the secant line from 1 to 4. Okay, first of all, let's check if we can apply this theorem, mean value theorem, to this function on the given interval. Let's go back to the mean value theorem. So we want f to be continuous on the closed interval 1, 4 and differentiable on the open interval 1, 4. Okay, let's go back here. Well, first off, 1, f of x, which is 5 minus 4 over x, is continuous on the closed interval 1 and 4. We can sort of like really say it, because the only problem that this function has, only problem point that this function has is x equals 0, right? Because you're dividing by 0. But 0 is not in here, right? 0 is not here. So to say like f is continuous, and if you don't believe me, just go ahead and then graph the function for x min to be 1, x max to be 4, you're going to see like you have a continuous graph. Okay. And then 2, is f differentiable? Well, let's check if we can find f prime. Okay, f prime is the derivative of 5 minus the derivative of 4 over x. Okay. Well, the derivative of 5 is 0. And then let's use the power rule for this rather than the quotient rule. You can rewrite that as 4 times x to the minus 1 prime. And then here the derivative is, well, put this 1 and subtract 1 from the power. You have another minus here. So 4 times x to the minus 2, that's 4 over x squared. So I can find f prime. The only problem to define f prime is x equals 0, but as I said earlier, 0 is not part of the interval I consider to apply the mean value theorem. So we're safe. F prime exists. F prime is a nice function 4 over x squared, right? So all 2 conditions are satisfied, and we can apply the mean value theorem, which is exactly what mean value theorem says. There exists a c, at least one c, such that f prime of c is attained, which is what? Slope the secant line. All right, let's just look at what f of 4 minus f of 1 divided by 4 minus 1 is. Okay, so let me just clean this. There we go. So let's just do this. What is f of 4? Well, f of 4 is 5 minus 4 over 4. And f of 1 is 5 minus 4 over 1 divided by 3. Right? So this is 4, and this is 5 minus 4 over 1. 4 minus 1 over 3, that is 1. Okay? So in other words, we're looking for c's for which f prime is equal to 1. And I know what f prime is, right? So f prime is 4 over x squared, so this would be what? 4 over c squared. And I'm solving 4 over c squared equals 1, right? Multiply both sides by c squared, you have c squared equals 4, right? And from here, you get c to be plus or minus negative 2, plus or minus 2. Well, you have to watch out because our interval is 1, 4, 4. Minus 2 doesn't belong there. So we only go with plus 2. So this one says that at x equals 2, or c equals 2, the slope of the tangent line is exactly equal to 1. And is that true? Well, yes, because the slope of the secant line, we just found that to be 1, right? Slope of the secant line. And then, and as you see, the same slope is achieved at x equals 2, or c equals 2. You can find that, you know, the slope, the tangent line at c equals 2 is exactly the same as the slope of the secant line, because these are 2 parallel lines, as you see. Okay. Any question? You can unmute yourself and ask your question if there is any. No question. I can't hear you, by the way, if somebody just unmuted the microphone. Okay. I don't have any time left to go through this, but you can just go through this example by yourself. We have 2 functions and 2 intervals provided to you, and you're going to determine if you can apply the mean value theorem. So all you're going to check is the continuity and differentiality on those intervals for the given functions. And if if all two conditions are satisfied in the description of the mean value theorem, which is in fact here, right? Continuity and differentiability, two conditions, right? So if all two conditions are satisfied, then you can apply mean value theorem. And at the end, you can conclude that f prime of c equals, like for this example, f of pi minus f of 0 divided by pi minus 0, right? And here in this case, f prime is cosine in fact, right? Cosine x evaluated at c, that's cosine c, equals f of pi minus f of 0 divided by pi. And you can calculate this, in fact, so this is sine pi minus sine 0 divided by pi. Use your calculator, and you will see that sine pi equals 0 and sine of 0 equals 0, so this is 0. So then you're looking for c's for which cosine equals 0. Use the same unit circle business to convince yourself that at pi over 2, cosine is 0. And in fact, that is the only point you have the slope of the tangent line achieved to be 0. Okay? So, and this takes care of the part that involves sine function. And you can do the same thing for part B, but make sure all two conditions are satisfied first. Okay, you have to sort of like write them up by yourself. Okay. Anyway, as I told you earlier, watch this video at my YouTube channel, AOOZER. It's already live over there, but after I stop the YouTube live, it's going to take some time to for YouTube to process it. So that's why you should subscribe to the channel. When it's ready, it's going to send you a link then you can start rewatching the video in your own convenient time. All right. Do you guys have any question before I go? Any question? I see 7 no's. Okay, there is no question. If you have any question, by the way, you just simply send me an email. And don't forget to take the quiz of today.